Perfect. Let's go then.
Okay. So the talk is Seeing in the Dark. It's basically developing a denoising architecture for the electron microscopy setting, but the architecture has applicability in other areas as well. So let's see. Okay, so firstly, I'll introduce the physics setting really briefly. So Professor Jones on the call is much better able to explain this than I am, but I'll run through it really briefly. Basically, you send a current of electrons towards a specimen. The electrons being charged electrostatically interact with the nuclei and they're deflected. What I'm interested in, or the specific area that I developed this algorithm within, is the high angle annular dark field. So it's where they're incoherently scattered quite widely out. And this means that the signal is quite low. So this is absolutely the minority of the electrons. The majority ends up going straight through with minimal deflection. These guys are very sharply deflected. This technique enables insane resolution. So it's a really effective tool for materials that are kind of crucial at the minute. Like it's suitable for battery and solar cell research and solid state catalysis and other chemistry things that I'm not really versed in, but it's exceptionally useful. So let's have a look at the problem from the physics point of view. We take images like these. Basically, the more electrons you use, the larger the current, the brighter and better the images are for material characterization. You get to see more details, greater delineations between atoms. The vacuum is darker between images, and you can just get more information from them. The problem is the more electrons you use, the more damage you cause your specimen. And there's plenty of materials that are really chemically interesting, but as a result, when you put them in is what essentially a small scale particle accelerator, they don't hold up all that well. So if you can somehow put these electrons in, or put these specimens in a lower intensity environment and still retain decent image quality, it really widens the range of materials you can characterize. But if you use less electrons, you absolutely incur image noise, and there's no getting around that. It's just an intrinsic nature of the amount of signal that you're using. And this noise can be pretty damning. It has this weird feedback loop that develops that when you're at the microscope trying to squeeze out the best image possible, the poor image quality affects your ability to tune the equipment. And so in addition to it being firstly noisy because of the amount of signal that you're throwing at your specimen, it's doubly ineffective because the equipment could be so much better tuned than that at the microscope, but that's just beyond you at the minute because you're working with images like this. Now, this is a very stark like opposite, or it's the complete opposite end of the spectrum entirely. Like this image here is 10,000 electrons per angstrom squared, whereas this is about 100. So it usually wouldn't go around this range because it's the same material, but I mean, Jesus, you can make out nothing of it. So let's have a look at the problem from the maths perspective. When you have this little signal, you incur Poisson noise. That's just the statistics of not sampling your distribution enough. But in addition to that, you quite often have Gaussian noise as well, which is noise that comes from the amplifier. Both of these noise regimes are present. Most denoising solutions only deal with one or the other. We need to deal with both if we're going to offer a tool that's actually effective at the microscope. But the tool needs to offer an in-painting, as in it can perform a slight interpolation, because your data can be, I guess, really haphazard because of the Poisson noise. Or haphazard is not the right word. It can be like it can be quite speckled because of the Poisson noise, but it also has this blanket white noise across the image that comes from the Gaussian noise. So it needs to be able to remove this and interpolate this to get the true underlying signal. The other problem is that the metrics that you use to tell you how well your denoising algorithm functions are pretty poor. All of them, from like the mean squared error to the peak signal to noise, structural similarity index, or the image enhancement factor, none of them quite do the job or conform to what's qualitatively obvious for us looking at the pictures. You know, when we can see this is clearly the best reconstruction, the metrics would disagree. And that's a bit of a problem. There's another issue as well, which is if you don't use the deep learning, you often have ambiguity in trying to perform the optimal reconstruction. So when you use unsupervised learning, and that's basically a host of techniques that like perform sort of dimensionality reduction, and you try and shave off dimensions. Your capacity to shave off dimensions the ability to systematize that it's not easy. We tried a number of ways of doing it, from like examining the entropy of the distilled data to the gradients, and it didn't work. There's too much ambiguity in it. But then if you go the other end, which is the pure deep learning, the pure machine learning approach, where you get it to draw on like a massive data set to distill it as best as it can, given what it's seen, this inevitably introduces artifacts into your reconstruction. So it'll see things that aren't really there. You know, it might see like an edge of an atom that doesn't actually conform to reality at all. It's just inferring what it knows from its data. So that can be a problem as well. And then all of them are slow. The non-ML approaches can vary massively as well. Like you can go hardcore tensor analysis, multilinear tensor analysis, and the problem blows up and you require supercomputers to deal with it. The machine learning approaches require insane training and simulations to get any kind of efficiency at all, and even then their generalizability is pretty poor. So the solution then is what we've termed the rapid eigenpatch utility classifier for image denoising. And there's more pictures to follow. This is the last boring word slide. But basically what it does is we first determine the point spread function. The point spread function, I'll go into exactly what that is in a second. But what this lets us do is it splits the image into patches. Now this allows us to narrow our analysis to a scale which circumvents global image properties or global material properties. It doesn't rely, by doing this, it doesn't rely on encompassing any knowledge of the crystal structure or anything like that. We can just focus on local analysis within the image. The next thing is to divide the workload. So if we wanted to work with the microscope, it has to be quick. So we need to have a quick gauge for the amount of data we're going to require and divide it in such a way that each patch of data fits into the working memory of the computer. We then use the unsupervised machine learning approaches. Again, I'll go through all of this in a sec to identify the key components of the data. We choose the components that are most useful and discard the rest. And then we just reconstruct. And as we place the patches back onto our canvas, we have to account for overlaps between patches. And this is essentially our problem. And I'll show you how each of the pieces fit together. So firstly, we have to find an estimation for the point spread function. What is that? Well, basically, so this is a picture from Hubble, and this is a picture of Betelgeuse, which is a massive, supermassive red giant. I think it's pretty close to us, meaning when we look at it, we are seeing its true width. Just like when we look at the sun, we're seeing its true width. But when we look to more distant stars, the impression of width here is false. These stars are so far away that they're functionally point-like in terms of like our angular field of view. This impression of width just comes from the like the imperfections in the optical system, and the fact that you can't have like a perfect optical system. That's where this is coming from, and it's exactly the same for atoms in the image, right? The deflection which gives us our signal comes from electrostatic interactions between the nucleus and the electron. But you know from analogies that you've probably heard through school and that you would have heard that, like, you know, the nucleus is like a ball at the center of a stadium and the electrons are like dust in the stands. If that's the case, then why is there an impression that they're somehow the gaps between them is comparable to the size of the nuclei themselves? It's just not the case. What's happening here is this is the best that the optical system can deliver us. So what we do first of all is we get a gauge for this width. This is a convenient width to choose for the patch size, and I'll explain why it's convenient later. But firstly, how to get it. So we use a function called the autocorrelation function, and you can think of this thing as taking two copies of a distribution and moving one relative to the other and seeing the extent of the overlap on moving at a certain displacement. So with this, for example, right, this is just a slice of the previous image. And when I haven't displaced this bottom guy whatsoever, the autocorrelation function takes like takes a value. This value will inevitably be its maximum, because if you displace it to any degree, it's not going to agree to the same extent as this. So when you move the bottom copy a certain amount, you have these blobs of intensity here, these point spread functions. You'll get to a point where you move the point spread functions so that they move perfectly out of step with the original copy's point spread functions. Now remember, this is of a crystal, right? A physical crystal. So there's a degree of periodicity here, and that's what we leverage to get out this this behavior. Because when you move it a certain distance along that same displacement, you'll get to a point where the intensities again overlap. No, they won't overlap to the same degree, because obviously you move your pixel and they're not you've moved your picture and they're not exactly the same point spread functions, but your autocorrelation function will again go to another maximum. What this lets us do is this lets us gives us a rough gauge for this width. So we don't actually need to model the point spread function. You can, but it's really too much for us to do at the minute, mainly because we are trying to do this live at the microscope, and to actually model it precisely is it's sort of excessive for what we need. We only need an impression of width, and the autocorrelation function provides that. So then what do we do? Okay, so we take out patches of exactly this size. This size is called the kernel, or the kernel size. But we notice that, like, for an image which is like 1,000 by 1,000 pixels roughly, that if you take out a patch at every pixel, and each one of those patches have, like, I don't know, 15 by 15 pixels in them, or it could even be 30 by 30 pixels, that the actual amount of data you require to, or memory you require to process all that data, it blows up. It gets really big, so big that it doesn't fit inside the RAM of any standard computer at the microscope, and we don't want to have to use supercomputers or anything like that. So what we do is we split up the workload. So you take the array of your image, you copy it to I guess a random array, and in this case, right, for whatever raw image this would have been, you'll see, like, it required 7 workload divisions, so that each one of the patches in their own right, together with the processing, any one of those patch stacks would have required would fit entirely within the RAM. So the patches corresponding to one are all extracted into their own stack, and we will deal with the processing of a given patch stack firstly. But you'll notice as well that when we take them out, there's certain pixels that are going to be sampled twice or 3 times in this case, and we have to address that overlap, but we'll deal with that later on. But the kernel size of 3 is a bit unrealistic here, but it's just for demonstration. So when we take out a bunch of different patches, we perform what's called randomized singular value decomposition. At its most basic level, it's just identifying the key components of the data. So if we take a look at what the components are here, there's the central blob, right, which we would imagine, yeah, of course, this is going to be a key feature of any data set where point spread functions are all over the place. But these subsequent features, they describe like I guess the edges of blobs, intersections between blobs, the diagonal intersections, and lines like these could include information about scan noise. So this is where, as your detector is scanning across your specimen, the specimen is kind of moving a little under it, and it can bring about these lines in it. But when you perform this analysis, it by itself and the eigenvalues that you get from this can be quite, I guess, vague in terms of where you make the cutoff. So for any first years here who don't know what eigenvalues or eigenvectors are, they're basically just the key features of the data. And the eigenvalues, like in this context, is its relative importance. If you take a look at this graph, in the literature, they refer to this point here as the knee, and it's where you think there should be the most drastic cutoff in eigenvector utility. But that's not really the case, because there's some useful information encoded in 6 and 7 and possibly even 8, but I mean, you're losing it by 9. And so if you are going to distill the data into these different components, there does need to be a cutoff. That cutoff often doesn't agree with what the numbers or pure randomized singular value decomposition suggests. So you need to layer on it with a different approach. Is there any questions so far? No? Okay, good. I'll keep going on. So, okay. So let's look at how we make the decision. We need to find a metric that works for us. So what we're looking at here is a graph of the denoising performance after having included a certain many eigenpatches, right? So this, obviously, at this point here, we would have included up until this guy in the reconstruction, and all of these guys would have been discarded. So yeah, we'd reconstruct each patch, but discarding its dependence on these more noisy patches. And we get a graph that looks like this. It obviously suggests that you need to include more than just the singular blob, because that doesn't encode any information about boundaries between the point spread functions. But you don't want to include too many, because you end up including things like this, which contribute just noise. Unfortunately, all of them, well, the majority of the metrics we tried were complete garbage. So like the mean square error was trash. It didn't even offer a critical point at all. Neither did the peak signal to noise ratio or the structural similarity index. They were all just trash. They didn't work. The best one we could deal with was best one we could find was the image enhancement factor. And even then, this the peak that this would offer would rarely, if ever, align with the reconstruction number that gave the qualitatively obvious best reconstruction. It was just off the mark. So we needed to make an addition to it. And so the way we did this is we divided out by the patch number to the power of C. So what this let us do is it let us first of all match the peak to the best number of eigenpatches to use. But secondly, it also increased the expressivity of the metric. So with this guy here, the critical point is not all that obvious. You need something where it's definitively pointing to a specific, it's definitively pointing to a specific eigenpatch number to re-include. Because when you're training models based on this metric and stuff, they're all based on gradient descent. And if your functions have no kind of expressivity in them, the descent and minima identification is really slow going and often ambiguous, and can lead you down to incorrect minima in your gradient descent stuff. But how do we actually determine that factor C, right? If the quantitative metrics didn't work, all of the metrics which I described didn't work, then how are we actually going to determine the C? Well, the way that we settled this is we asked experts. So this is the expert response for, I guess, the enhancement after a certain dosage has been applied to a material. So these were simulated images. And we got the response distribution from experts. Funnily enough, it actually aligned really closely with non-experts, which was a bit shocking, but it worked. And what we were able to do is try out different values for C and see which one of those values gave us the closest alignment of this peak to the red average within our expert responses. At this point, it probably seems a bit hand-wavy, but at the end of the day, we have to come back and ask, what are we optimizing for? In this case, we are trying to assist the experimentalist at the microscope. It doesn't make sense to use a quantitative metric of like mean square error or peak signal to noise. Even if they're quantitative, we're like, at that point, you're like hiding behind a veil of objectivity that it doesn't map to reality, right? None of those metrics actually give you the best image. In this case here, we're creating our own metric, and we're fitting it to the expert's actual perception rather than just some arbitrary metric, which ultimately, because all of the metrics we tried were so different, to decide on one is just, again, another subjective decision. So you may as well outsource this decision to the wider scientific community. So what happens once you rely on this approach and you choose the value for C that expert consensus arrives at? This is the reconstructive capacity, right? So for the 10,000 electrons per angstrom, you can remove a lot of that Gaussian noise that's around the place, and it enhances it a fair bit. For the 100, you have a slight issue that it's beginning to, the in-painting aspect of it, where it would try and write, let's say this, I don't know if you can even see it, there's like a single pixel there that's in the vacuum between two, I guess, silicon atoms. And it's trying to represent that as its own atom because it's forcing a linear combination of eigenvectors on it. And at that point, it becomes a little bit unsuitable, but you can layer on this with further approaches like variation regularization, fix that up quite well. And even with that in mind, it still actually performs pretty well. There's silicon atoms here which are very well distinguished, and it still gives you a better sense of what you're looking at than the original. In the 500 electrons per angstrom, it's really shining. This is pretty bad data, and it's enhanced quite significantly. Basically, I'm going to give you an overview of why all of the things fit together the way they do. None of this might seem novel on its own right, but the way that it's stacked together is what lets it be so effective. So we take the noisy image, we perform the point spread function estimation that I talked about before. So what this does is, regardless of the magnification of your image, it lets you identify a kernel size that standardizes the scales of the features that you extract. And I'll explain why that's important in a second. But basically, so we start with the point spread function. We take out the stacks corresponding to a given number. We perform that random singular value decomposition. So we identify all of the principal components. Now, these principal components are going to be blob size, regardless of whether the resolution of your microscope allows a given atom, let's say, to be represented by 7 pixels or 40 pixels across. And that's useful because when you give it to your neural network to decide whether or not these guys are useful or useless, it only has to deal with features the size of a point spread function. So your neural network, because it's so, because it can be guaranteed that the features are going to be a particular scale, it can be very, very small. And because of that, it can be very, very fast. So what's happening here is you've got a massive amount of data. this performs the dimensionality reduction, and it's there instead of the pure. Okay, so in a pure deep learning perspective or scenario, they would just take this and run it through some convolutional neural network or autoencoder that would remove basically all of the noise at the risk of introducing artifacts from your data set. What we're doing, because we're trying to be fast, is we're leveraging the distillation of features through dimensionality reduction. And in the distilled space, we are performing this discrimination. Also, what's crucial about the deep learning that we do employ is that it never at any point meddles with the data. So all it ever does is classify the components that have been identified here. It never has a chance to, I guess, have any sort of input from its training set. It never has the chance to be unphysical in what it suggests. It just says it has a binary output. It's either yes or no, given the state of the eigenvector that was presented to it. This here, these are the two same patches, right? After having discarded the useless stuff and kept the useful eigenfeatures, or eigenpatches. And so the patch train, I'm not really going to go into that at the minute, but myself and Lewis, we've come up with a clever way of calculating this on the fly very quickly. And what that lets you do is, when you're going through your stacks, if at the microscope another image has finished scanning, you can return the intermediate result by calculating this terrain on the fly, not going through all patch stacks. Like in the example I gave previously, there was 7. Here you could cut it at 3 and take that image and present it out as it stands. And it oftentimes works pretty well, but it just, again, enables a major speed up. That's pretty much it. We've got a paper in the works, but it's looking good. And it's working pretty fast. At the minute, it's written in Python, which is unfortunately a bit slow because Python's an interpreted language. But we're going to be recoding it to C, which should be pretty quick, or Python. And at that point, we can expect to see live reconstructions. So before I finish up, I'd like to just give a quick thanks, right? So first and foremost is the Advanced Microscopy Laboratory. You can't really do this kind of analysis if you don't have access to seriously high-end equipment. And if that elite equipment gives you perfect or great data to work with, like, I'm not a hardcore experimentalist at all, but I do like messing with data. And if you want that, you need good equipment. With all of this data, and because of the nature of it being on our doorstep, instead of having to book in with advanced like telescopes and that, as you would if you were working with data in the astrophysical context, it's a great opportunity to mess about with deep learning techniques. Also, the field is full of low-hanging fruit, especially from a data physics point of view. And if you hit it with advanced techniques like the randomized singular value decomposition we looked at there, like this clever arrangement of architectures that complement each other in a particular way, there's lots of low-hanging fruit that's there to be taken. And also, the group itself, the Advanced Microscopy Laboratory group, it's supervised or run by Professor Jones, and it has Laidlaw scholarships all over the place, pretty much every year since Laidlaw's been here. There's summer internships going, plenty PhDs at the minute, and postdocs. The group is growing massively, and Professor Jones is an unreal supervisor to work with. Like, at every stage, didn't matter what time of night I was texting him. He probably shouldn't have texted back, but he'd have an answer for me straight away, and he's always got your development in mind. So if you are interested, in getting into data physics, this is a very rich realm for you to do so. So that's pretty much it. If anyone has any questions, just ask.